Welcome to the welcome to the PH1105 lecture. In this video segment, we will talk about standing sound waves and normal modes. So, in this figure below, we're showing here is an experiment where we can have a speaker, a diaphragm that vibrates in response to the sound from the speaker, a stoppered end for the tube, and then we can have gas that we can pump in to the tube, and we can also have sand inside the tube that will be displaced by the sound wave to form nodes and antinodes. So when we have a pressure node, because we have seen the derivation of this equation where the pressure is given by minus b, the derivative of the displacement with respect to x. We know that a pressure node is always a displacement antinode, and a displacement and a pressure antinode is always a displacement node. So as shown in this figure over here, where you see here, this is a displacement node because the particle is not moving at all over time, and you can see that the particle next to it is on this side, on the left is coming towards it, on the right is coming towards it. So now you have a high pressure you have high pressure at this displacement node, and then later on you have the particles are moving away, so you have low pressure at the displacement node, and in fact the pressure variation is the largest at this displacement node. And then for a there's the same thing happens on the other side. This is the other the successive the neighboring node, displacement node, and this is another displacement node. So all we have to keep in mind is that the pressure node is always a displacement antinode, and therefore where do you think the sand will be piled up? It will actually pile up at the displacement nodes, because here the sand doesn't move at all. It is being pushed by sound waves on both sides. So this is what we expect to see. So these are displacement nodes, and this is a displacement antinode. So the sand is actually being taken away from this point here. Okay. Now, if I have a loudspeaker and I direct it towards a wall, and then the sound wave will be reflected, and you can set up a standing wave just like you did in the tube. Then what distances could you stand and hear no sound at all? So because it's a standing wave, and at a wall you necessarily have a displacement node, because the air molecule cannot move into the wall. Of course it can move away from the wall, but because it cannot move into the wall, so the better option is for it to remain still. So that's why walls are always displacement nodes. So it cannot have displacement here, zero displacement. Now, because it is a displacement node, it is a pressure antinode. So at this point here, at this displacement node, you have the highest pressure fluctuation. Same thing here, this is a displacement node, but they have the largest change in pressure. And our ear responds to pressure, not displacement, and that's why here we hear the loudest. Here we hear the loudest sound at the wall, and therefore, in order to hear no sound at all, we need to be at the displacement antinode, which is 1/4 of a wavelength away, 3/4 of a wavelength away, and also 5/4 of a wavelength away. Okay, now so all this proceedings discussion is to set up our discussion of musical instruments. So the simplest musical instrument that we can talk about is actually the organ pipe. Now, organ pipes come in the different sizes that produce different tones, tones of different frequencies, and the reason they do so because they have different lengths. The organ pipes can have different lengths. They can have different cross sections. Although the cross section is not the most important thing here, we've seen from the discussion earlier, it is actually the length that is important. How the organ work is that you have air that is being blown by a blower from beneath. It will go in here, and it will go through a small opening called a mouth, and it will vibrate. It will vibrate, and it will cause, and you create sound. And this sound here, because this is kind of like stoppered, this will be a sorry, because this is not really stoppered, so that at this point here, the air can have the largest possible displacement. So this is the displacement NT node, this is a displacement node, which is a high pressure region. This is a displacement NT node, this is a displacement node, and at this particular snapshot in time, it is a low pressure region. But half a cycle later, it will become a high pressure region. So this is how basically organ pipes work. So the blue color is, like I said, the blue color is supposed to indicate the pressure variation, but the node and NT node refers to the displacement of the air molecules. Now, for a pipe that is open at both ends, so in a sense, the organ pipe, of course, is open on the end that you don't blow air into, but it is also open on the end where you blow air into, because if it is not open, then you could not blow air into it, and therefore we can treat this somewhat like a pipe that is open at both ends. Now, for a pipe that is open at both ends, for a pipe with an open end, the open end must be a displacement NT node and must be a pressure node, and the reason for that is because this pressure here must be equal to the atmospheric pressure, otherwise there will be airflow. So at steady state, you should have here the same pressure as the atmospheric pressure around it, which is why it must be a displacement NT node, because a pressure node is a point where the pressure does not change with time, and therefore it must be a displacement NT node. The same kind of argument applies to the other open end, and therefore we can go from maximum displacement to maximum displacement, maximum displacement to maximum negative displacement, and therefore we have the situation where we have an NT node on this end, an NT node on the other end, and we can then have a node in the middle end. And this length here, the length of the tube, must therefore be equal to 1/2 of the wavelength, because we have gone from minimum most negative displacement to most positive displacement, and we need another half a wavelength to come back to the most negative displacement. And if we have the second harmonic, so this is the fundamental frequency harmonic, if we are looking at the second harmonic, then again the open ends must be NT nodes. Then what we do is we insert one more NT node in the middle. Then the node will of course separate the NT nodes, so there will be a node here, and an NT node in the middle. And if you look at this case, you see you go from maximum positive displacement to maximum negative displacement back to maximum positive displacement. Therefore, the length of the tube is equals to 1 wavelength. Okay, so 2 lambda over 2. Okay, and when you go to the third harmonic, again the two open ends must be NT nodes. You insert 2 NT nodes in between. Therefore, you insert also the nodes to separate them. So you have 3 nodes separating 4 NT nodes, and therefore we find that from NT node to NT node is lambda over 2, from NT node to NT node is lambda over 2, and from NT node to NT node is lambda over 2. Therefore, this length of this pipe is then equals to 3 times lambda over 2. Okay, so therefore we can derive a formula for the frequency of the harmonics in a pipe that is open on both ends as N times V divided by 2L. Okay, where V is actually is the speed of the wave, and N over 2L is 2L over N is the wavelength of the harmonic. Okay, so this is how we take into account the boundary conditions to work out the frequency of the harmonics in a pipe that is open on both ends. We can also have a pipe that is closed at one end. Obviously, it cannot be closed at 2 ends, because if we close at 2 ends, we cannot set up sound vibrations inside. But we can close at one end. For example, suppose this is an organ pipe, and you close it at one end, then the other end is open. So the open end must be an NT node, but now the closed end, because there can be no displacement, must be a node. So you can see that you go from maximum positive displacement to 0. Okay, over the length of the tube, and therefore the length of the tube is only 1/4 of the wavelength. Similarly, when we go to the next higher harmonic, we realize that we go from NT node to node to NT node to node. So therefore, we go from the maximum to the maximum positive to maximum negative back to 0. So we only we only move through 3/4 of the wavelength. So and therefore, you can the same arguments go for the fifth harmonic, and therefore we can say that the frequency of a pipe that is closed at one end is just equals to NV divided by 4L, where now you have restrictions on the integers. They must be odd integers. Whereas for the earlier case, you see that the integers run from 1, 2, 3, so odd and even all included. Okay, and then the fundamental frequency of this pipe that is closed at one end is V over 4L. Okay, and then here let's go through an example to end this segment. We know that the speed of sound is 345 meters per second. Some people give it 343. Some folks will give it 340. It's okay, just take whatever you're given and use it. And the fundamental frequency of a stopped pipe, stop means that it is closed at one end, is 220 hertz. Then the question, part one of the question asks, how long is the pipe? We know that the fundamental frequency of a stopped pipe, we know that for a stopped pipe, the fundamental mode actually has the length of the fundamental mode has a wavelength such that the length of the pipe is equal to 1/4 of the wavelength. So therefore L stop, so we know this, F1 is equal to V over 4L. Therefore L stop is equal to V over 4F1, which is 345 meters per second divided by 4 times 220 hertz, and that is equal to 0.392 meters. Okay, and the second part of the question wants us to find the second overtone of this pipe that has the same wavelength as the third harmonic of the open pipe. So how long is this pipe? So again, we make use of the formula. Okay, so we want 3 times. We want the second overtone, which is actually the third harmonic of the closed pipe. Sorry, no, wrong. We want the second overtone of the pipe to have the same wavelength as the third overtone of an open version of this pipe. So this is the frequency of the open pipe, and it is equals to 1100 hertz because the fundamental frequency is 220. So this is what it is, and it is related to the speed of the sound wave and the length of the open pipe. In this way, therefore we work out the length of the open pipe to be 0.47 meters.